Okay, so we were looking at the edge chromatic number of a graph. And last time we showed an upper bound. So we called this edge chromatic number chi prime, and we showed that it was less than or equal to 2 times delta of G, where delta of G is the maximum degree minus 1. The maximum degree of a vertex. And the proof of this was like just kind of a straightforward greedy algorithm proof. So now I'm going to write down a theorem which is a lot stronger. So this says if, okay, right. So by the way, this holds for any graph. And we saw some examples last time also that kind of illustrated that having multiple edges has like a really dramatic effect on the edge chromatic number. So what happens if we exclude multiple edges? So if we just have a simple graph. So if G is a simple graph, then we have a much stronger statement. So it says that delta of G is a lower bound on the edge chromatic number, and the upper bound is actually only delta of G plus 1. So for a simple graph, you only have 2 options for the edge chromatic number. It's either equal to the maximum vertex degree, or it is 1 greater than the maximum vertex degree. Okay, so what is the reason for this inequality? Why is this true? Yeah.
Well, if you look at the line graph, and specifically around like the vertex of like max degree,
Yeah.
that vertex will have delta G edges coming off of it.
Yeah.
And each of those delta G edges will be connected to each other in the line graph.
Yeah.
So you'll have some complete graph on delta G vertices on the line graph. And so the line graph will need at least delta G colors.
Yeah, exactly. Yeah. So if we look at that vertex of maximum degree, all of the edges coming out of it will require different colors because they're all touching each other. So edges at the vertex of max degree require different colors. Okay, and then the proof of this half. So this is actually quite a lengthy proof. And I was going to include it, and as I was like writing out the lecture notes for it, I was realizing that it was gonna take like 45 minutes. And I feel like this point in the semester, like no one has the stamina to like witness a 45-minute proof. So I don't think it would be like super interesting or enjoyable to like go through that, but it is in the book if you are interested. And there's also a different proof on Wikipedia as well. So if you don't like the proof in the textbook, there's like another one you can look at, but it's also like pretty lengthy. So we're gonna skip that, but you do have this. So I do think that this statement is pretty nice. So like basically all this is saying is if you have a simple graph, the edge chromatic number only has two options. And there is something nice that you can say. So using the results that we already have for bipartite graphs, you can show that if the graph is bipartite, then you're forced to have equality here on the left. So we will prove that. So let's prove this theorem. It says if G is bipartite, then chi prime of G is equal to delta of G. Okay, so for the proof, we already proved earlier on when we were studying bipartite graphs that every regular bipartite graph has a one factor, where recall that regular means that every vertex has the same degree. So if H is a regular bipartite graph, this gives a proper this fact gives a proper delta of H coloring, edge coloring by induction. So I'll just draw a picture for this. So let's suppose we start with a regular bipartite graph. So in this picture, I'm drawing K33. We know that it has a one factor. So I'll draw the one factor. Then I could remove that one factor and I still have a regular bipartite graph. And now I can apply the result again to this bipartite graph. So this is a regular bipartite graph. It has a one factor, so I'll take that out. And then we get this. And what's remaining is also a one factor. So in total, this would give me an edge coloring, a proper edge coloring of the original graph. Okay, are there questions about this part? So this is just a special case of the proof. Okay, so then it suffices to show that for every bipartite G, with maximum degree K, there is a K regular bipartite graph containing it. Sorry, I just realized I don't think I ever shared my screen to the Zoom, so I'm gonna do that now. Okay, so good. So the lecture, from now the lecture will be recorded. Okay, so right, so if we are able to show this, if we are able to show that there is a K-regular bipartite graph H containing it, then that H has a proper K edge coloring, and using those exact same colors, I can look at the graph G inside of H, and that will produce a proper K edge coloring of G. Does that make sense? Okay, so now, so this is all we have to argue at this point. So step one, so G may not have partite sets of the same size. So I'm gonna add vertices to the partite set of smaller size. Okay, so then this thing will not be regular. So if we did add vertices, they currently have degree 0. So it's probably not going to be regular. So that means that so step 2, which we're gonna like iterate a bunch of times. So if the graph is not regular, then each partite set has a vertex with degree less than K. So we'll add an edge with those two vertices as endpoints. And we'll repeat step 2. So I guess part 3, repeat 2 until the graph is K regular. And that finishes the proof. Okay, are there questions about this? Would it help to like work through an example? Okay, so let me start with this graph G, where, okay, so from this portion, I've already produced a 3 coloring of K33, right? So let me draw that over here. So this is our this is our 3 edge coloring of K33. So let's say my G looks something like this. Okay, so oops, I think my coloring is not good. I need to switch up one of these. Okay, hold on. Let me just start over. Whoops. Okay, so we had the red matching, and then one of the matchings was like this. And the last matching was like, yeah, the opposite thing. Okay. So G has a vertex of degree 3. Yeah. Yes. Is that high enough? Okay. So G has a vertex of degree 3. So I need to produce a 3-edge coloring of it. And the argument, obviously this is a small example, so we could just do it by hand. But we'll just like go through the argument. So how the argument works is I'm going to view G as a subgraph of some 3 regular bipartite graph. So step 1 is I need to add vertices to even out the 2 sides, because we have no shot of being K regular if and bipartite if the 2 partite sets do not have the same size. And then I'm going to say, okay, so if G is currently not K regular, which it's not, then that means that there's some vertex on the left and some vertex on the right that do not yet have degree K. So I will just add the corresponding edge. Okay, so I'll just add in edges to fill this out. By the way, this argument did not rely in any way on this bipartite graph being simple, so it's okay if I add in multiple edges when I do this. Okay, so now I have this, and G is inside of, so I've like filled out G to become K33. I have an edge coloring of K33. So I'm going to use that to get an edge coloring of my original graph G. So all I'm going to do is copy the colors over. So that edge becomes green. That edge becomes green. This edge is blue. And then the other 2 are red. Okay, so that's how I get my coloring of G. Okay, are there questions? Okay, so now we're gonna shift and talk about something called Hamiltonian cycles. So I'll write the definition. So a Hamiltonian cycle is a spanning cycle of the graph. And we'll say that a graph is Hamiltonian if it has a Hamiltonian cycle. Um, so I think last time we said that, an Eulerian circuit in the graph gave a spanning cycle of the line graph. So this is just an observation, like a correspondence between Eulerian circuits. We talked about way back in the beginning. So these give Hamiltonian cycles. So this is Eulerian circuits of a graph G, give Hamiltonian cycles of L of G. Okay, so we'll do an example. And actually, I'm going to make more room for the example. Okay, so what I'm going to draw is the edge graph of the dodecahedron. Oops. Okay, so my challenge to you is to draw a Hamiltonian cycle in this graph. Okay, did anyone find one? Yeah,
Start at vertex one. And then go clockwise around to vertex 19.
okay.
Go one ring into vertex 16.
Uh-huh.
Then go counterclockwise and leave it vertex 4 around sort of this layer of the cycle.
Oops. Yeah.
Enter in one more further into vertex 10. Go clockwise and leave it 13. And then just sort of expand outwards with the 1.
Nice. Yeah. Yeah, I think yes, this is good. There's a lot of ways to do this, but this is like one way that you can draw a Hamiltonian cycle. The textbook mentioned like a game where I think it was like one person picks 5 edges or something like that, and the other person has to like provide a Hamiltonian cycle on this graph that contains those 5 edges. I don't know if the exact number was 5, but yeah, seems kind of fun. But yeah, okay, so this is an example of a Hamiltonian cycle. Are there questions about the definition? Okay, so there's no easily testable characterization known for whether or not a graph is Hamiltonian. So what we will study is some necessary conditions and some sufficient conditions. And for this, the rest of the lecture, we're going to just restrict our attention to simple graphs because like loops and multiple edges won't matter for whether or not a graph is Hamiltonian. Because like, yeah, it wouldn't matter, right, if we had multiple ways to get between those 2 vertices. Or if there was a loop at one vertex, that also will not change whether or not the graph is Hamiltonian. Okay, so let's look at some necessary conditions. Okay, so first I'm just gonna make the observation that every Hamiltonian graph is 2 connected. So why is that? Why is every Hamiltonian graph 2 connected?
You like comment about at least like one and then one else, so at least there's 2 connected.
Yeah, so first of all, like it's connected, right? Because I have a spanning path. I can so I can get from any vertex to any vertex just by going along that cycle. And then as another sort of like what was, we had a criterion for 2 connected, but I think it's exactly what you're saying, that like there's between any 2 vertices, there's like 2 internally disjoint paths, right? So if I pick 2 vertices in this graph, so like let's say I did 8 and 16, there's 2 ways to get from 8 to 16. There's like moving one way around on the cycle and moving the other way around on the cycle. So since the cycle gives internally disjoint paths, between every pair of vertices. So this is a necessary condition for a graph to be Hamiltonian. It would have to be 2 connected. But it's possible for us to strengthen this condition. So let's look at an example. So the question will be, when is a bipartite graph Hamiltonian? So take a second to think about what this would mean, and then we'll discuss after. Okay, so did anyone think of a condition for when a bipartite graph would be Hamiltonian? Or just a necessary condition? Yeah,
I don't know if this is enough. I think the necessary condition that, minimum vertex degrees too.
yeah, that's for sure a necessary condition. Yeah, because you have to go in and out of every vertex. Yeah, so necessary. Any other conditions? Yeah,
I wasn't, that both vertexes have to have equal size.
yeah, so why is that true? So your cycle is gonna pass alternately between the two partite sets. So half the cycle is gonna be in one set and half of it is in the other set. So if you're hitting every vertex, then the two partite sets have to have the same size. Yeah, so like K, the complete bipartite KMN, oops. This is gonna be Hamiltonian if and only if M is equal to N. And I guess they also would have to be greater than 1, because then there's no cycle if it's just K11. Okay, so this intuition kind of gives us a way to extend this to a necessary condition for all graphs. Or so this is going to be a proposition. And it says that if your graph G has a Hamiltonian cycle, then for each non-empty subset S of the vertices, the graph G minus S has at most S many components. So this is like kind of similar in flavor to like the Hall's condition and all of that stuff. So let's see the proof of this. So let's think about our Hamiltonian cycle. So if it's leaving a component of G minus S, so when leaving a component of G minus S, the Hamiltonian cycle has to go to S. And any arrivals to S will then therefore use distinct vertices of S. So therefore, we have to have at least as many vertices in S as there are components of G minus S. Okay, so maybe I'll draw a picture. So let's say this is our set of vertices S, and maybe there's some edges in here. And we have components of G minus S. So if I were to, I don't think I even can draw a Hamiltonian cycle in this. Okay, maybe that improves my chances. So if I draw a Hamiltonian cycle in this, then every time I'm going from one of these components back into S, I'm going to use up a vertex of S, basically. So if there's too many components lying outside of S, then there won't be enough ways to enter S. Does that make sense? Let me try and draw. Oh my gosh. This actually just still may not be Hamiltonian. Okay, it's only supposed to be a necessary condition. Yeah, we're not going to be Hamiltonian unless I add. We need a lot more. But anyway, so yeah, are there questions about this? Okay, so this condition, so this finishes the proof. This condition actually is enough to guarantee two connectedness. So here's the reason. So if I delete one vertex, how many components do I have left if this condition is satisfied? So this is like size of S is 1. Yeah. Yeah, exactly. Yeah, um, so if the condition is satisfied, then G minus a single vertex has one component. So it's connected. Okay, so here's like what we have shown. So if G is Hamiltonian, um, that implies two connected. And Hamiltonian implies this condition. I don't know, I'll just write it. So size of S is greater than or equal to number of components of G minus S for all S subset of the vertices. Okay, so we have that Hamiltonian implies these two things, and also this condition implies two connected. This is kind of like the way the implications go. So now I'm going to show you some examples to show why these arrows don't are not if and only if. So examples. Okay, so the first one, so let me number the arrows. So the first example is going to be so why arrow 1 is not an if and only if. So this is going to be an example satisfying this proposition. But not Hamiltonian. So this is the graph. This is an example from the book. I don't know if this is like the simplest possible example. Okay, so we have like this kind of thing on both sides. And then in each of these, we have like this kind of thing going on. Okay, so why okay, so take a minute to think about why this satisfies the proposition, but also why it's not Hamiltonian. Oh, sorry, this one does not satisfy. My notes are kind of confusing. So this, okay, so what is this an example of? This is an example of a bipartite graph whose partite sets have equal size, but it is not Hamiltonian because it fails the above propositions. Let me. But you can still think about why it's not Hamiltonian. So let me rename this example. Okay, so why does this graph fail the condition in the proposition? Yeah.
You delete like the ones at the side, like, conforms S's.
Yeah, so this is an S of size 2, but G minus S has 3 components. So this example just illustrates that this condition for bipartite graphs is not enough to guarantee Hamiltonian. And then the second example, so this is the one that satisfies the condition from the proposition, but has no, but is not Hamiltonian. So satisfies. But not. Okay, so let me draw this graph. Okay, so take a minute to think through why this one isn't Hamiltonian. Does anyone have a reason for why this isn't Hamiltonian? Yeah.
Well, you have the three neighbors of the middle vertex.
Mhm.
And for each of those on one side coming in or out of those vertices, you'll have to like touch the middle vertex, but of course you can't touch it 3 times.
Yeah, so like these three vertices all only have degree 2. So we don't really have any options there. We have to use the 2 edges that are adjacent to those vertices. But then that requires me to use all 3 of those edges that are connected to the central vertex. And so that that means that it won't be possible to make a Hamiltonian cycle. So yeah, and then presumably like there's only 7 vertices here, so you know you only have to check 2 to the 7th things to see if this is true. But it's symmetric, so you know it's even less than that. But yeah, so presumably you could also check this condition. So non-Hamiltonian because we would have to use all edges adjacent to vertices of degree 2, which forces the use of 3 edges adjacent to the central vertex, which is a contradiction. We can't have that. Okay, are there questions? Maybe going back. So I want to like go back to this triangle of implications. So we have an example that tells us why we can't reverse that arrow. And this first example, this is 2 connected. But we showed that it doesn't satisfy this. So this is an example of why this arrow is not an if and only if. And then do we have an example of something that is 2 connected but not Hamiltonian? That should be pretty easy to come up with. Does anyone have one in mind? Yeah. Yes. Okay, yeah. So this is example 1. And this also is violated by example 2. Yeah. Okay, so now we're gonna switch to talking about sufficient conditions. For a graph to be Hamiltonian. So the idea here is that if every vertex has enough choices, then the graph will be Hamiltonian. So like here, it was a problem that we had vertices of degree 2 because then that forced us to make particular choices of edges that ultimately led to the graph not being Hamiltonian. So if we have more choices at every vertex, then there's sort of like always somewhere that you can go. And that's going to be kind of the idea behind these sufficient conditions. So what we will prove is that if the minimum degree of any vertex, little delta of G, is greater than or equal to the number of vertices of the graph divided by 2. Which is like quite a lot. It means every vertex has an edge to like more than half of the vertices. Then the graph is Hamiltonian. So first, let's think of an example of that shows why we can't make an improvement to this statement. So why won't a smaller lower bound work? So why won't a smaller minimum degree work? So I'll give you a minute to think of an example and we'll talk about it. Okay, does anyone have an example? So this is examples of not Hamiltonian and the minimum degree is one smaller than the one given in the bound. Yeah.
For the case where n of g is odd, and that's like the floor of n of g over two,
Okay, yeah, what was your,
you can like take this like a central vertex, which will be like your cut vertex,
mhm,
and then on either side of it, do like a complete
yeah,
graph of size n minus one over two.
so it's like this one.
Yeah.
For example. Okay, yeah, so the minimum, okay, so here n is 5, so you could just put complete graphs on either side. So maybe I'll do K4s on either side to make the example. It's easier to see how to generalize it. So, okay, so n here is 7. So that means that, and delta is 3. And it's, okay, so this is not Hamiltonian because it's not even two connected, right? It has a cut vertex. But the bound, so n over 2 minus 1 is equal to 2.5. So or yeah, maybe I should write this as delta of g is greater than or equal to. So in this case, delta of g is greater than or equal to n over 2 minus 1, but it's not Hamiltonian. Yeah. Does anyone have another example? So this is like one strategy is like gluing complete graphs at a central vertex. Yeah.
Could you take that central vertex and like extend it?
Yes, I think that works. Yeah, so this will also still not be Hamiltonian.
Then
Oh, but then the minimum does yeah, because then n raises by 1, and then we have 3.5 is this number. So I think this actually doesn't work. So the other one that I had written down was complete bipartite, where the two partite sets have size 1 different from each other. So for example, 3 vertices on one side and 4 on the other. Oops, wait, did I get all of them now? Okay, so this is K3, 4. So the number of vertices again is 7. The minimum degree is 4. And then n over 2 minus 1. No, but this will be Hamiltonian. Wait. Oh, no, it won't, because the partite sets have different sizes. Wait, now I'm confused. Because n over 2 minus 1 is going to be 2.5 again. Ah, sorry, I got the minimum degree wrong. The minimum degree comes from the vertices on the partite set of larger size. So the minimum degree is 3 again. But yeah, exactly. So this can't be Hamiltonian because, like we said before, our bipartite graph can only be Hamiltonian if the two partite sets have the same size. So we have partite sets with different size, so it's automatically not Hamiltonian. And the numbers satisfy like the constraints that we had. Okay, are there questions about these examples? Okay, so now we'll prove the theorem. So the theorem says that if G is a simple graph with at least 3 vertices, which, like, unfortunately, this assumption is necessary because you can think of examples on small numbers of vertices that will satisfy this but not end up being Hamiltonian. So if G is a simple graph with at least 3 vertices and the minimum degree of any vertex in G is greater than or equal to the number of vertices divided by 2, then G is Hamiltonian. Okay, so let's prove this. So this is going to be one of those kind of funny proofs where you uh, this is going to be one of those kind of funny proofs where you have to make like a maximality argument and you use like the property of the graph being maximal in the proof. So first we're going to like restrict our attention. We're going to prove that it's like satisfactory to look at some kind of like maximal, some notion of maximal graphs, and then we will use that property to like do the proof. So and it's going to be by contradiction as well. So it's like a little bit confusing. Okay, so towards contradiction. Let's let G be a non-Hamiltonian graph which satisfies the hypotheses. Okay, and then I'm gonna say that G is maximal Hamiltonian. Or sorry, maximal non-Hamiltonian. If adding any edge joining non-adjacent vertices would make the graph Hamiltonian. Would make the graph Hamiltonian. Okay, so that's just what I mean by maximal non-Hamiltonian. So if there's a way to add, if in any way you add an edge to the graph, you would make the graph become Hamiltonian. Okay, so if the graph that we started with was not maximal, so if this graph G, which satisfies the hypotheses but is non-Hamiltonian, is not maximal, so, okay, so this is like basically the overall strategy. We're going to show that such a counterexample must be maximal, and then we're going to use the maximality in some way to make a contradiction. So right now we're ruling out the possibility that G is not maximal. So if G is not maximal, then there is some edge we could add to it, and it would still be non-Hamiltonian. And in addition, it would still satisfy this condition. Delta of G is greater than or equal to N of G over 2, right? Because all that could have happened is, so the number of vertices stayed the same. I added an edge, potentially that increased the minimum degree of some vertex. So that means that we would still satisfy this. So if I continue repeating this process, so I just keep adding edges. So if I continue adding edges, until no more can be added, then I've obtained a maximal non-Hamiltonian graph that satisfies the hypotheses. So, okay, so where are we at? If I started with some non-maximal counterexample, I can use that to obtain a maximal counterexample. So I'm going to then go ahead and assume that G is maximal. Okay, are we on board with this? So, okay, so now I'm going to work with this maximal counterexample G. So let's consider two non-adjacent vertices in G. So let's let U and V be non-adjacent vertices in G. Then the maximality of G implies that G has a spanning path from one to the other. So why do we get this? So if we were to add in that edge, UV, then the graph would become Hamiltonian. So then I have a Hamiltonian cycle. And so deleting that one edge would give me in G a path through the whole graph. So I have something like, so here's my graph G. I have one vertex U and one vertex V. and then some sequence of vertices in the middle of it. Okay, so I'm gonna call this one V1. This is V2, and so on up to, this is Vn minus 1, and this is gonna be called Vn. And what we're gonna do is use this spanning path to make a spanning cycle. So this will contradict the fact that this graph was supposed to be not Hamiltonian. So let's observe that if a neighbor of U directly follows a neighbor of V, so if I have like U is connected to VI plus 1 and V is connected to VI, then there is a spanning cycle. And we'll see it in the picture. So let's let this one be VI and this is VI plus 1. So let's suppose I have an edge, two edges like this, that crisscross and they go to vertices that are adjacent to each other. Okay, does anyone see how to make a spanning cycle in this case? If I have this situation. Do you have the? It's gone. Okay, so we could start at U. Let's follow this edge to VI plus 1. And then I'll follow the path to get to V. And then I'll take this way back. Okay, so, so this is that's my spanning cycle. Okay. Okay, we'll finish this next time. I think we have a little bit too much left to just like squeeze it in the last 30 seconds. So okay, so your midterm is due tomorrow at 5 p.m. I have office hours today, or you can reach me over email if you have questions about it. And otherwise I will see you on Tuesday.
Yeah.